So in this video I'll be talking about degenerate semiconductors. So basically what happens at very high doping levels. So it's really important to understand how much is considered high. So we'll look at what it mathematically means to have a highly doped semiconductor, and also we'll look at what is the physical significance and how it impacts the device performance. So firstly we'll start looking at the energy band diagrams, and we know that as we increase the doping levels, the Fermi level moves closer to the conduction band in case of a n-type semiconductor. So mathematically we can tell that if EC minus EF is greater than KT, that is, if the Fermi level is far away from the conduction band, then we call this as moderately doped. Or in other words, we call this condition as non-degenerate. If the Fermi level gets closer to the conduction band, that is, if the distance between the Fermi level and the conduction band becomes lesser than KT, then we call this as highly doped. Or in other words, this condition is called degenerate. And in most of the semiconductor problems, a commonly used approximation is the case of non-degeneracy. That is, we mostly consider that the semiconductor is moderately doped. And the reason for that is, for a moderately doped semiconductor, it is actually easy to calculate the carrier concentration. So what I mean is, the carrier concentration is actually given by the integral of density of states into Fermi energy function for a given range of energy levels. And the density of states is actually proportional to square root of E minus EF. And we know that the Fermi function is given by 1 by 1 plus E power E minus EF by KT. So basically this integral becomes, so this integral is commonly called as the Fermi integral. Under the approximation that EC minus EF is greater than KT, that is, the Fermi level is far away from the conduction band, under this approximation, this integral actually just reduces to an exponential function. So therefore, the carrier concentration can be easily given by the constant times the exponential function. So this way it's easy to find the carrier concentration in case of a moderately doped semiconductor. But in case of high doping, we cannot use this approximation anymore. So therefore, in order to find the carrier concentration, we'll have to evaluate this Fermi integral. Now let's look at the plot of this exponential function and the Fermi integral and see why the limit for this approximation is KT. So this is the plot of the exponential function and the Fermi integral. So the y-axis is actually on the log scale, and the dotted line actually represents the exponential function, and the solid line represents the Fermi integral. So from this graph, we can see that till the point where EF minus EC is equal to KT, that is still here, we can see that both the exponential and the Fermi integral have the same behavior. So in this region, the Fermi integral and exponential has the same behavior. Once EF gets closer to the conduction band, that is, once EC minus EF is lesser than KT, we see that the integral and the exponential function start deviating. So under this condition, we can't use the exponential function to actually calculate the carrier concentration. So we will have to solve the Fermi integral. So this is what it mathematically means to have a highly doped semiconductor. So now let's try to understand what is the physical significance of having such high doping levels. So let's consider a block of silicon, and suppose we are doping it with phosphorus atoms. At very low doping levels, we see that the phosphorus atoms are far apart from each other. Of course, you can have a case where two phosphorus atoms are very close to each other, since the doping is a random process. But since the level of doping is very low, or it is moderately doped, the probability of this happening is also lower. So now if I increase the doping of phosphorus, that is, now if I have more number of phosphorus atoms, now the probability that the phosphorus atoms are close to each other also increases. That means the distance between the phosphorus atoms is decreasing. And we know from band theory of solids or from molecular orbital theory that if two atoms come close to each other, their atomic orbitals will be combined to form molecular orbitals. That is nothing but the discrete energy levels will actually form into energy bands. So what I mean is, if you look at the plot of the density of states versus the energy, we know that in the conduction band it is proportional to square root of energy, and in valence band it is approximately proportional to the square root of energy. So in case of a moderately doped or lightly doped condition, we see a discrete level ED that is close to the conduction band in case of a n-type semiconductor. In case of a p-type semiconductor, we see a discrete level EA that is close to the valence band. Now as we increase the level of doping, the atomic distance between the dopant atoms decreases, and instead of having this discrete energy level, now we will have a band of energies. So that is, now we will have donor energy band. Now what this does is, this effectively reduces the band gap of the material. Earlier, the band gap was defined by the difference between the bottom of the conduction band and top of the valence band, that is denoted by Eg. But because of this donor energy band, now the band gap has been reduced, that is given by Eg prime. And we know that the intrinsic carrier concentration in a semiconductor, Ni, is actually proportional to the band gap of the material. Now as the band gap reduces, the concentration of intrinsic carriers also increases. So how this affects the device performance is, if you look at the expression of leakage current in case of diodes or transistors, we see that the leakage currents are actually proportional to the square of intrinsic carrier concentration. So as this Ni increases, the leakage current in these devices also increases. We commonly hear people telling that as we increase the level of doping, the leakage current actually increases. And this is the physics behind why that statement is true. So this reduction of band gap from Eg to E prime is what is called as bandgap narrowing. So this is one of the effect of highly doped semiconductor. So let's again take a block of silicon and dope it with phosphorus. So usually doping is done either by diffusion or ion implantation. So as mentioned before, this is a random process. So if we increase the doping, there is a possibility that a bunch of phosphorus atoms can get grouped in one place, and on the other hand, the number of phosphorus atom in some locations can be less. And we know that the phosphorus atoms inside the silicon lattice ionizes, so this gives a free electron and it gets positively charged. So the total number of electrons will be equal to the number of dopant ions. So even though the entire silicon is electrically neutral, but because of this grouping of phosphorus atoms, we will see local potential variations. So we can see that this part of silicon is more positively charged compared to this part of silicon. So based on this local potential variation that is happening because of unequal charge distribution, and this is coming because of the randomness of doping, we will see that the conduction bands and the valence band get stretched into the band gap. So what I mean is, again, if you look at the plot of the density of states and energy, so ideally the band gap is clean. We do not see any localized states apart from the ones introduced by the dopant atoms. That is, near the conduction band it is due to n-type dopants, and near the valence band it is due to p-type dopants. But at high doping levels, we see that the conduction band actually gets stretched into the band gap. Similarly, the valence band gets stretched into the band gap. Now this has a very big impact on the performance of MOS transistors, because this is one of the reasons why the subthreshold slope of MOSFET increases. So in other words, the MOS transistor becomes slower, and this stretching of energy bands into the band gap is what is referred to as Bandtails. So we can see that high level doping actually degrades the performance of MOSFET, but it is important to understand the context in which high level doping degrades the performance. So in this case, the high level doping in the channel region actually degrades the performance of the MOSFET. In case of source and drain junctions of a MOSFET, it is very important to have high doping, because there we have to form ohmic contact between the metals and the semiconductors. So these are some of the ways how high levels of doping can actually degrade the performance of the devices. So that's it for this video, and see you in the next one, and thanks for watching.